So to not delay you further, we're going to get started. So welcome, everyone. Thank you for coming to this installment of the ICARL seminar series. For those of you who are new, this seminar series consists of a 1-hour talk followed for some networking event with food provided by our sponsor, DeepMind. So today we're very excited to have with us Tim Rocktäeschel, who is team lead of the openness research team at DeepMind, associate professor at UCL, and research scholar at the European Laboratory of Intelligent and Learning Systems, who is here to tell us about the challenges of NetHack. So Tim, the stage is yours. Thank you.
Thanks so much. Yeah, it's great to be here. I guess I can't remember the last time I stood in front of, I guess, an audience with actual 3D people. So it's nice that you all came. So yeah, I'm going to talk about the NetHack Learning Environment and its challenges for open-ended learning. This talk is roughly, I guess, split into 2 parts, NetHack and then some research that we did inspired by NetHack. If you have any questions, any clarifying questions, please feel free to just ask them during the talk. And if you have more philosophical, questions, more harder questions that require more discussion, let's leave them to the end. Okay, so in the beginning, I just want to establish some of the limitations of commonly used reinforcement learning environments and why we need something else to drive research. So unless you've been living on a rock, there's this method called reinforcement learning, or it's I guess a class, a family of methods. The idea is here you have an environment and an agent. The agent performs actions in the environment and it observes a new state and also reward, and it tries to maximize expected return in such an environment. And again, unless you've been living on a rock, reinforcement learning has been driving a lot of great successes in artificial intelligence research. For example, we have now AI that's superhuman in StarCraft, in the game of Go, in all these Atari games, and in Dota 2. So this is all really impressive. At this point, you might be saying, okay, what's left to do? Alexander Webb for There Were No More Worlds to Conquer. Say again? Mathematics, yeah. So I also heard there's now, I guess, more and more work in terms of using AI for theorem proving. Yeah, I agree. And I guess it's exactly also the point I'm going to make. Obviously, we're not done, right? We still have research to do. And to just take Atari, for example, as you probably know, Atari has a really tiny action space. There's only a few things, right, in every state that you have to kind of control. And it's also one of these, what we would call a singleton environment. So every time you play an Atari game, it's going to look pretty much the same. And it is also a deterministic environment simulator. It means over time, you can actually literally memorize what kind of actions you should be doing in these environments. There are certain ways around this, sticky actions and whatnot, but I'm not going too much into detail. One specific Atari game, which is called Montezuma's Revenge, was a game that actually served as a challenge for exploration for many, many years. So if you look into this original Nature paper by DeepMind, this was actually one of the games at the very bottom of the list. So that was one of these games where reinforcement learning couldn't do anything. By now, there are also methods that can crack this game, but they make a heavy use of these properties of this deterministic simulator, right? So they learn basically how to return to previously visited states and then explore from these previously visited states. So what I'm going to say, and I guess for many of you, maybe that hopefully resonates, specifically if you're working, for example, in robotics, eventually we need to have our agents stepping outside of the simulation. So solving StarCraft 1, 2, solving chess, Go, Atari, and so on. These are all great accomplishments in my view. Obviously, I don't want to downplay them. But we want agents that can eventually serve us practically in the real world. And the reality is a much noisier, more dynamic, more variable environment than a Go board or an Atari game. So it doesn't mean that we have to stop doing research in simulated environments. I think they're still very important to drive fundamental AI research. But we need to start dropping some of these assumptions in these environments. We need to do something different to make progress. We must close the gap between the real world by progressively removing simplifying assumptions of these simulators. So for example, we might be interested in environments that require us to transfer external world, domain, and common sense knowledge in order to actually progress learning in the environment. The environment itself might involve natural language that you need to deal with. The environment might have a photorealistic observation space, making computer vision a bottleneck, for example, of progress in the environment. There might be a constant stream of novel observations. Every time you start a new episode, maybe things look very different to anything you've been seeing before. The tasks might change, the dynamics of the environment might change. There might be a really large, even unbounded action space of things you can do in the environment. And the environment might not provide you with any reward function, or if it provides a reward function, it's a very noisy one or extremely sparse so that you can't do much with it. And probably there are even many other things. So what happens if we start dropping these assumptions? What are simulation environments that we could be using? One environment that I think is very exciting is, for example, Minecraft. This has been now used quite a bit already for AI research. It is what we would call a procedurally generated environment. Every time you start a new game of Minecraft, this world is generated, so no game will really look exactly the same as any of the games before. And you have a lot of stuff to do in this environment, right? There's a lot of objects, a lot of affordances you have to learn about. So this is great. But I guess I'll argue that this is a quite slow simulator. So ideally, we would have something that encompasses a lot of these challenges, but is extremely fast to simulate so that we can actually do academic research with it. What are techniques that we need to have in order to then learn in such complex open environments? Well, there are more and more techniques that we would, I guess, put under the category of open-ended learning. We already know that these open-ended learning methods work. They're an important ingredient of many of the recent RL breakthroughs. For example, self-play and AlphaGo, population-based training in AlphaStar and Excellent, intrinsic exploration methods like R&D, Write, Amigo, Novelty, E3B, and novelty search methods like Go Explore. This is the one that was actually used to crack Montezuma's Prevention in the Atari game. There's also more and more work on trying to achieve strong generalization by training on a really vast problem space through procedural content generation. So the environments like ProcGen, Minecraft, Minigrid, also this excellent paper introduced a really vast, basically procedurally generated problem space. And the idea is once you've trained on such a vast space, you can basically interpolate between any problem. And then at test time, if I give you a new problem, you somehow know how to kind of attack it. And at the same time, if you look into robotics, or even using reinforcement learning for controlling nuclear fusion plasma, you'll find techniques like domain randomization to robustify the policies learned through RL. And they also, I guess, direct ways of trying to robustify such policies through data augmentation, like in AutoDrag. So all of this is nice, but we need better open-ended benchmarks to measure progress. I already mentioned Minecraft here on the right-hand side. There are other procedurally generated benchmarks that people have been developing over the last few years. For example, on the top left is the obstacle tower challenge, where you have some 3D jump and run, and every time you enter a new level, this level is going to be procedurally generated, and it's not going to look like any of the levels you've been seeing before. And then here in the middle, you have OpenAI's ProcGen benchmark. This is a suite of 16 different games. Each game is, again, procedurally generated. In every episode, something will change, like the textures or the assets. Sometimes even the environment dynamics, like in this boss fight here in the middle, might change. So you really have to constantly generalize to kind of novel situations. So this is great. My only problem is, again, this 3D simulator obstacle tower challenge, as well as Minecraft, they're extremely slow to simulate in terms of steps per second, whereas the Atari games that have been used for a long time in reinforcement learning research, they're extremely fast to simulate. So we can actually plunge through them in tens of thousands of steps per second. One simulation benchmark that's really fast is this OpenAI ProcGen benchmark, but the problem here is that it actually is relatively limited in terms of the things you can be doing. You can do in this environment, right? It doesn't give you the same vastness of objects to deal with and environment dynamics to discover. All of these games are still relatively simple. So could we have something that is maybe almost as rich and complex as Minecraft, while as fast to simulate as these Atari games or this OpenAI ProcGen benchmark? So the thing we found that satisfies these properties is NetHack. Maybe quick show of hands, who has played NetHack before? You have played NetHack before? You remember when it came out? 1987, I think. Wow. You were an undergrad then. Okay. Anyone else who knew about NetHack or played NetHack before? Yeah, a few people, very few. Okay, fantastic. Who has ascended in NetHack? Anyone who actually succeeded in this game? I did. Okay. So anyway, so this is a really old game, right? 1987. This game is played in a terminal. So the way this looks like is literally like this, right? And it's a so-called dungeon crawl game. You're thrown into a dungeon. You're this character over here, this @ symbol. Everything is rendered in text. You can walk around. You can try to find all kinds of items that help you, like amulets and weapons and armors and potions and scrolls and wands and rings and spell books and all kinds of tools and whatnot. And the goal is you have to descend very deep into these procedurally generated dungeons up to, like, I think 50 levels, retrieve a certain item, and then come up again. And it's extremely unforgiving. So anytime you die in this game, it's game over, right? You have to start again from the beginning. It's procedurally generated, and nothing looks exactly like it looked before. And it's one of the hardest games in the world, basically. So the nice thing is, because it's rendered in a terminal, right? There's not much computation wasted on this. We can simulate this insanely fast. Okay, so let me just give you a bit deeper understanding of, like, what makes this an interesting environment for reinforcement learning research. First of all, there's a clearly defined goal: descend the dungeon and retrieve a specific amulet. In Minecraft, you'd have to define these goals, right? It's an open kind of sandbox game, but here we have a clear goal that eventually we hope AI can crack. As I already mentioned, it's procedurally generated. So every time you start a new episode, things look different. And it's insanely rich. So there's hundreds of monsters and item types that you have to learn about. If you want to win in this game, you have to accumulate a lot of knowledge about the underlying environment dynamics of this game. Humans learn from external knowledge sources like the NetHack Wiki to master this game. There's, as far as I know, not a single recorded instance of a human being able to play and win in this game, tabula rasa, by not, like, looking up these kind of spoilers or these kind of textual information about how to master this game. So that's true, but people did send around, I think, text files that would record some of this information, right? But yeah, this was a huge step, right? Having actually the NetHack Wiki has 3,000 documents about all these kind of different things. It's a huge resource of a wealth of information about this game. It's also a very long game, so it takes a expert player who's specialized in winning this game as fast as possible, something like 10 to 20,000 steps. And an average really good player solving this game takes roughly 50 to 100,000 steps. If you compare that to StarCraft 2, with 3 actions per second is what they used in the paper, and 15 minutes of gameplay, that's 2,000 steps, right? So this is 1 to 2 orders of magnitude longer episodes than in the StarCraft 2 benchmark. That makes, it comes with a whole lot of problems, right, in terms of credit assignment, long-term planning, and so on. At the same time, it runs extremely fast. So I think there's actually even an outdated number. I think we're now even much quicker than this. But at the time of publication, this was 14,000 steps per second with a pretty standard deep reinforcement learning infrastructure. It uses, I think, 2 GPUs. So that allows you to train for 1 billion steps a day. So every day of training, our agent would have 1 billion interactions with this environment. It's still really popular. So there are over 5 million online recorded games, a lot of expert games there as well. People still play this. It's actually still under development. There's a development team that releases relatively regular new updates to this game, and it's open source, which makes it amenable to us for actually turning that into a reinforcement learning environment. So what's the goal of the game? Again, it's kind of finding this amulet, offering it to the in-game deity. This is how Dali mentioned how this would look like, so that you're not just looking at ASCII characters. And I just want to spend another few minutes just to convincing you how complex this environment is. At some point in this game, you have to cross over to Medusa's island and go to the next dungeon level. So you're starting over here, and Medusa is over there. If you want to get there, you realize actually this island is surrounded by water. And now my thing here stopped working. Okay, that's great. Okay. The moment you step into water, if you have any metallic items, they can rust and corrode. If you happen to have a can of grease in your inventory, you can apply this grease to these metallic items to prevent rusting and corrosion. You can also apply this grease to a sack that you might have in your inventory, and that turns that sack into a waterproof container, which is good for all the scrolls and spell books that you have, because if you go into water with those, they will turn blank and be useless. The sea can constrain a kraken. If you encounter that kraken can grab you and just drown you, and you're instantly dead, and you have to start this entire game from scratch. And just take note, this is already I think level 20 something, so this is after probably 2 days of gameplay, so really annoying. If you happen to have this kind of grease, you can also grease the hero's armor, which prevents the kraken from actually grabbing you.
But this is not public knowledge in 1987.
Yeah. This is something you had to work out back then. Nowadays, people like me look on the NetHack wiki and get spoiled, basically. But you're right. The real challenge is, I guess, learning about this the hard way. Once you're actually over on this other side, you enter this room, Medusa's gaze will petrify the hero, turning the hero into stone. And again, it's a source of instant death. You have to start the game from the beginning. If you happen to have a towel, you can cover the hero's eyes, blind the hero, and that allows you to fight Medusa while being blind. You could also, if you happen to have a mirror in your inventory, use the mirror to petrify Medusa using her own gaze. So I guess the only thing I want to say, please believe me, this is an insanely complex game, right? There's all these kind of environment dynamics implemented by the development team over the last 3 decades, basically. It's constantly also updated. There are things in there that you could use to exploit the game to then have an easy time later on in the game. All of these things over time have been removed. There were people writing bots, I think 10 years ago, that were able to solve this game. Then the dev team sat down, removed some of these exploits, and now we don't have any kind of symbolic system that is able to solve this game. Okay, so now what is a NetHack learning environment? Well, we just take NetHack. Sorry, there's a question.
Yeah, you're making this seem like the hardest game. Just wondering if you can spend a second talking about what makes other games more challenging.
So there's I think an article by The Guardian listing the 15 hardest games in existence. NetHack is one of them. What makes games like Go or StarCraft so interesting and challenging for our research is that you're actually playing against a human, right? At some point, here it's not a multiplayer game, right? So you're just fighting against the game, not against other humans who can start to adapt to you, who can start to, even if you're an expert player, start to find exploits for you. This is not one of these games, right? Yeah, it's a bot, but once you know about these things and you're prepared, then actually fighting Medusa is easy. The problem for AI is to actually figure out these things, right? I mean, relating back to the point that was made earlier. Yeah. 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 Yeah, so of these 5 million online recorded games that you could, for example, use for learning from demonstrations, right, which would be an interesting research avenue, not all of these games are compatible with the newest version. Some things you see there, you now are not valid strategies anymore because you can't use the exploit. Or, yeah, some things might have changed. Some things might have been, yeah, just buffed or so. Yeah. Okay, yeah. Say again? No, but we'll get there. Okay, so what is now the NetHack learning environment? It's quite simple. It's basically an OpenAI gym environment plus some predefined tasks plus some baseline deep reinforcement learning agent. If you are working in DeepRL, you like this interface, you want to have some kind of way to instantiate the environment, to reset it, to step through it, to render it. This all can be done within like 5-6 lines of code, and then you have actually the running environment in your terminal. You can, start to train your agents. You can even debug your agents. You can look at the episodes of your agents. So it's really nice in that regard. We have a number of tasks defined. Obviously, the actual task that you care about is, can you succeed in this game, which is, can you ascend in this game. And this is, yeah, this is extremely, extremely hard exploration problem. So that's why we thought for researchers to get started, we define a number of simpler, much simpler tasks, right? Just finding the staircase on the first level, finding some milestone in the game, the oracle, trying to maximize in-game score, which kind of somewhat correlates with progress, but it's also not perfect either. So you can get started with these tasks, or you try to directly go for, I guess, ascension. We also have a baseline model, a very simple one, is a convolutional network over these characters in this dungeon, plus some features that correspond to, for example, the agent's health points, the armor class, experience level, and so on, as well as another inductive bias where we kind of heavily bias towards things that are close to the agent by this additional CNN that is constrained around the center of the agent. What's also quite interesting is that NetHack gives you quite often these in-game messages, right? You do something and it tells you you just killed a gnome. So it's quite interesting, I think, to think about how to utilize this kind of natural language information to help exploration. Okay, so as I said, we get to something like 14,000 steps a second with a pretty standard DeepRL approach, and this is corresponding to something like 1.2 billion steps a day. Then you have all these different tasks. You can look at how RL is doing for these different tasks. And I'm not going too much into detail, but basically what I'm saying here is that for these individual tasks, DeepRL, for different character classes as well, it progresses, right? It learns something, it gets better at doing things. It achieves a score on average, I think, of 600 here. It goes down dungeon levels up to, average dungeon level 5 out of like 50 something. And it also levels up. But all of this is really 1% of the game, right? This is very early in the game, and it's far from being solved. And I'll get to the state of the art in a minute. I just want to spend another few minutes on this NetHack wiki, which I think is such a fantastic resource. This is over 3,000 documents that you find online that, as your colleague said earlier, didn't exist 20 years ago, but now it's there. It lists all kinds of attributes for all kinds of items. It gives even some info boxes here that provide a lot of useful information, and it also provides some strategic advice, right? Quite high-level strategic advice about how you should go about certain monsters and items in the game. So do you really need the wiki? Ideally, you can do it without, but as I mentioned, I don't know of anyone who was able to solve this game without being spoiled in some form or another, whether that's through a wiki or back then through some kind of telnet conversations, whatever it is. So I would say yes. There's so many ways to die in this game that players even came up with a specific term for that, yet another stupid death. Here's a list of a few things that mean this game ends prematurely and you have to start from the beginning. So maybe it's a good idea to think about like how we utilize such domain-specific knowledge that humans have been accumulating in natural language form to help reinforcement learning. So since you're asking what's the state of the art, we did run a challenge at NeurIPS last year, the NetHack challenge. For us, it was a really exciting moment because we said, okay, actually, we don't care what kind of method you throw at this, right? You use deep reinforcement learning, fine. You think you can better by actually handcrafting a bot, fine, right? Because we know this happened in the past. We know people were able to solve this game 5 years ago with a bot when certain exploits were there. So maybe people can do this again with this updated version of NetHack. So we let these different approaches basically compete with each other. And we asked the question, what is going to be better, right? Deep reinforcement learning, which has been so successful in so many other areas, or is it going to be people writing actually symbolic bots? And what you see here is the top performing systems at the competition. Last year, I should also add, we had, I think, over $10,000 in prize money. So people were really incentivized to crack this. And symbolic bots by far outperformed all the deep reinforcement learning approaches. And on top of that, none of these symbolic bots got really far in the game either, right? So they also stopped at average level 10 or so. Yes?
How many submissions did you get for symbolic track versus the other?
I think it was pretty even out. You can still look this up. This submission, I mean, all the leaderboard and so on is still online on AI Crowd. You can also read through our report where we go a bit much into detail about these things. But for just to be clear, for the deep reinforcement learning community, this was a bit of a shock, right? There were lots of people who thought, surely deep reinforcement is going to take this home, right? But we actually see, I think there's a threefold threefold difference, right? Just in terms of in-game score for this game. So it's a bit of a wake-up call, right? Just vanilla deep reinforcement doesn't seem to cut it here. Okay, any other questions about NetHack? Okay, so then as researchers, you might say, okay, this is way too challenging, right? I want to make progress on this. I will still want to do fundamental AI research or deep reinforcement research, but clearly there's no sense in like just throwing this at the entire game. So we have you covered. There's another paper we presented at NeurIPS last year called MiniHack. And MiniHack has been done by all these fantastic people, like Mikael Semvayan, PhD student in my lab, also Jack, who's here today. The idea is, could we create a lot of much smaller tasks, but utilizing all this richness and vastness of NetHack? And the way this works is you have a description file where you could literally draw a level in ASCII characters, like over here. And you can use all kinds of things from NetHack, like lava and water, and you can create all kinds of mazes. Here, it's my attempt to create a little mini Earth, right, with trees and ice and whatnot. And you inherit all these complex environment dynamics for NetHack, but you can now create really targeted scenarios that test your AI method. And this description file you can think of basically a probabilistic program. So you can create specific locations to put items or monsters in there, but you can also start to have randomness in this level creation. For example, here I'm just placing 3 random objects in random locations, some random trees, and then also some river that can be either from lava, water, or ice going from here to here. And then once I actually create an episode and reset it, it would always look slightly different, right? So you can actually test for generalization of your RL method or your RL agent in this environment. It's a very easy way for you to create really big, rich task distributions without having to go to the full game of NetHack, basically. So we have also access to a lot of high-level commands in this NetHack description language. We can create mazes, we can create rooms and connect them automatically through these commands. We have all these hundreds of monsters and objects and dungeon features that all come with different, again, environment dynamics that you would have to learn about. Yes? Yes, so it's exactly like NetHack. It's just a way for you to define a lot of custom tasks that you can use to really get at the frontier of what the RL method currently can do and try to push that. Yeah.
In terms of software, then common software, or was MiniHack curriculum?
No, it's NetHack, and it's just hooking into this description language that NetHack uses itself actually to define the entire game, just making that very accessible so that you can create all kinds of custom levels. Yep. Yeah, so there's this is a graphical user interface for NetHack. You could also play the entire game at NetHack using this. It's not written by us. This is also part of NetHack. If you're a hardcore NetHack player, you would frown upon this. You would always just play this in ASCII, like in the Matrix, right? At some point, you're like, I just can decipher that in my head. But yeah, so as part of the observation space, I think I'm getting to that. I'm not sure if I get to that here, but basically we give you the ASCII characters if you want. We give you these renderings if you want, and we even have for each thing that's displayed here a natural language description, like it's a tree or it's a yellow dragon or so. You could also access that. So you get all of that as part of the interface of this reinforcement environment. Yeah. We have a number of tasks already implemented that you could use. Some of them are navigation tasks that become increasingly challenging here. You have to actually do some hide and seek. There's a really powerful monster, and you have to find the stack race really quickly while hiding behind these trees. We also have a lot of skill acquisition tasks. So this is really for testing some of the state-of-the-art exploration techniques that actually are all biased towards navigation and not so much about like actually discovering different skills. So here you have tasks like this where you have to get to the staircase, but there's a river of lava, and you either have to find some ring of levitation or some boots of levitation, or get some boulder moved into this, or getting some frost horn to turn the lava into stone. I mean, there's lots of different ways basically for solving these tasks. That allows us to actually test some of the state-of-the-art exploration methods. A lot of submissions for NeurIPS and also ICARL have been already using some of these tasks here to see whether we can drop some of the limiting assumption of existing exploration methods. On top of that, if you've been using mini-grid or, for example, DeepMind's Boxoban levels, you can easily, very easily import them basically into NetHack. And then once you have them, you can start to make them harder, right? By, for example, turning all the walls into lava, and then the moment the agent moves into that, it's dead. Or you can populate these rooms with monsters and whatnot, right? So you can really take existing benchmarks for exploration, hierarchical learning, skill acquisition, get them imported in here, and then start to make them gradually harder to test the boundaries of current research methods.
When you say we can port, it's like, will we also be some of only the ones that have in the default unit, or it could be one of the already maybe implemented for unit, and is there an automatic way to transport any?
Yeah, so we have an automatic way to, I think, get almost every mini-grid environment in here, except for the ones where you have different colored keys, because that doesn't correspond to anything in NetHack. But for many of them, we basically have an automatic way. Similarly, here we had an automatic way to turn all of these Boxoban levels into NetHack levels.
So Boxoban could move the object.
Yeah, I mean, that's the whole task. You have to move basically the boulder, in this case, over a fountain. And if you have moved.
I don't understand. What's the analogous thing in NetHack?
Well, there isn't an analogous thing in NetHack. I mean, there's Sokoban in NetHack as well. But the way we port this over here is these are fountains. They come from NetHack, but then you have a boulder. You move over the fountain. If you moved all the boulders on all the fountains, we have an automatic check to say, yes, you solved the level. Yeah, we just basically piggybacking on NetHack. Okay, so where can this be used? Well, for testing classical reinforcement learning, exploration methods, for transfer learning between different NetHack environments. Maybe even you can pre-train a policy in there and then transfer it over to the full game of NetHack. You could use it for unsupervised skill discovery, for unsupervised environment design, which I'll get to in a bit. Or I think also very interesting direction is to investigate language-assisted RL, right, where you try to transfer some knowledge from NetHack, from the NetHack wiki, or from these in-game messages in NetHack. Again, this comes with a lot of baseline agents and is also shipped with this connection to RLib to really provide you with a lot of kind of things to start from to do research. Okay, so now let's, how are we on time? I guess, yeah, quite good. So now let's move over to some actual research, right? The first thing to notice here is that you won't see much work that is actually done on NetHack. But a lot of the problems that I described here are actually inspired by these challenges in NetHack. So the first paper I want to talk about is prioritized level replay. This is from my PhD student, Minxi Zhang, and in collaboration with Edward Greffenstedt at UCL, DARC. And the idea here is that, well, like NetHack, right, there's a lot of problems that we could cast as problems or environments with procedurally generated content, like these OpenAI ProcGen benchmarks. And that means every time we start a new episode, the environment varies in some form. I already talked about this quite a bit. And what we can now utilize is the fact that these procedurally generated environments, they usually have some generator that's seeded, right? So if you put in the same seed, you would get out the same environment. And we can test for generalization by taking some unseen seeds, right, at test time and seeing if we can now do well in these unseen environments. And I think this concept of procedurally generated environments is somewhat general, right? I mean, we have this in the full game of NetHack, but even some robotics tasks you could kind of see under this lens, right? You have a certain configuration of the blocks in the environment, and if I let the robot do stuff and move all these blocks, and then I reset it and try to actually get exactly the same configuration of blocks as before, right? Then I guess you could see this as kind of seeding this robotics environment, although I'm sure there's a lot of pushback on this crude simplification from roboticists. And in other games as well, like card games like Hanabi, right, you can see the deck of the cards as a specific configuration of this environment. So the primary preliminary motivation for our work here is that if you have a procedurally generated environment and you generate a lot of instances of this environment, surely some of these will be simpler problems, and some of them will be very hard problems. So how can we utilize the fact that in this problem space, there is a certain ordering, right, of difficulty that's maybe also really contingent on the current agent capabilities. So for example, here in mini-grid, there's a level where we have to pick up this key, get through this door, get to this ball. There might be another level where we first have to get the key from this box, move away some obstacle, and then get through the door. Or maybe there's a really hard instance where we have to go to a different room. There might be two boxes that we have to check where the key is there, and then we still have to move these obstacles to find this goal. So how can we kind of automatically learn a curriculum that moves us through this problem space? And this is exactly what prioritized level play is doing here. Initially, the agent can't solve any problem, but based on its own value loss, so its own prediction of how well it would do in the environment as opposed to how well it does, it starts to prioritize easy levels because that's where it randomly got some reward. And then the moment it starts to learn more and more on these easy levels, at some point it starts to become quite adept at it. So that means its own value prediction is going to go down, right? Because it knows it can already do these things well, but because it now has learned these useful skills, it's actually able to also tackle some of the slightly harder environments where now the value loss is going to go up because it's predicting it's not going to do anything good, but actually it does, occasionally get to the goal. And then that gets us at some point even to the really hard problems. So this is the underlying, this is what we want, right? This is the underlying motivation for this level replay idea. So the way this works is you first have some distribution over all these levels that's uniform. This is, by the way, how in I guess 90% of the cases people train RL in procedurally generated environments. They just assume a uniform distribution of all the levels and then they just randomly sample from it. We start with that as well. We try out an episode right from this distribution, and we collect a score. And this score should represent how useful would it be for the agent to actually learn in this environment again. And the way we're going to parameterize that is using the regret. So how well did the agent do as opposed to how well it could have done. And the way we're going to approximate that is via the agent's own value loss, the agent's own value prediction. And that's where there are these kind of four different cases. One is the agent predicts it's going to do really well and it actually does really well. That's not very interesting, right? There's not much to learn from. Another one might be actually it predicts it's going to do really badly and it's actually done really badly. So it's also, again, not something quite interesting to learn from. But then there are these other two cases, right, where it either overestimates or underestimates its own ability. And these are the levels that we want to keep, that we then want the agent to try out again in the future. Right, so we keep a buffer basically of these seen levels. We're going to record this score, this kind of potential for learning in the future for each of these levels. And we're also keeping around some staleness where we basically track what was the last time we actually tried this level. If we didn't try a level for a long time, there's a good chance that this score is now really off policy, not really corresponding to the true learning potential of the level. And we might want to try this level again. This could also help with catastrophic forgetting in these environments. So from these scores, we derive a new distribution. This is not uniform at this point, right? This is going to be somewhat shaped that we can now use to sample from to find those levels and replay those levels that have high learning potential. And then in the beginning, we have some binary decision to make. Should we sample a completely new level, or should we just train on the sample from the levels that we've already seen in the past? So that's basically it. Just to go slightly into the formalization of this. So this is for the agents that we use, PPO agents, the general advantage estimate that we use to parameterize this value prediction. From that, we using, I guess, softmax, we're getting this probability distribution over the scores for these levels. We also have the staleness, which is the total number of levels we've seen so far minus the last time we've seen a certain level. And then the replay distribution, the actual replay distribution is some interpolation between the two. So we tested this out on OpenAI ProcGen benchmark. These are 16 diverse procedurally generated environments. I already talked about this. We have pixel observation space, and we then generalized to unseen episodes, unseen levels at test time. And what we see for these ProcGen environments is a pretty dramatic improvement in terms of both sample efficiency as well as generalization ability. So up to 28%, or exactly 28% improved generalization performance. And if we combine that with a state-of-the-art augmentation technique, UCB drag, then we actually see a 76% improvement over a number of baselines. So it's a really strong result in terms of closing this gap between training and testing, and also leading to much more sample efficient learning. And then similar, even more dramatic results we get when we actually look at these much harder instances of these simulation environments.
In these cases, does the C capture just the configuration of the environment, but also visual techniques?
All of this, the seed kind of completely determines how you're going to generate this environment, including what kind of assets to use and the position of objects and so on.
That's people, right?
Yeah.
So the buffer of environments is actually buffer of initial states that is initialized by
no, I think it's I mean, it's somewhat independent of the actual RL method. So it's really just keeping around a buffer to say, okay, if I reset the environment, should I reset that to a uniformly sampled, completely new environment, or should I use one of the levels, the environments that I've seen before, right? But it doesn't initialize. I mean, you're then starting in the same start state because that's also determined by the seed, but there's nothing corresponding to the specific RL other than we use the value loss of that specific, derived from that specific algorithm. Okay, so then we also tried it in a simple environment mini-grid, which has these kind of discrete difficulty settings. The only reason we do this is to, well, first of all, confirm again that this works, but more interestingly, I think we see now can actually, because we know what kind of seeds correspond to what kind of difficulty of the environment, we can actually track how that distribution over these different categories of levels changes over time. So we see in the beginning things being relatively evenly spread out, and then you see actually easy levels going down, harder levels being used more, and then somewhat later during training, mostly, I guess, mid to hard levels being used. So that's just, again, to confirm that there's actually an automated curriculum that's implicitly created through this level buffer. Okay, so then let's move over to a more recent work that we have presented at ICML this year by Jack, who's here, and then also again, Minchi, and Michael, and Mikael, on evolving curricula with regret-based environment design. So that builds upon this prioritized level replay and another work that we've done in that space to have more control basically over this automated curriculum. So the starting point here is that there are really interesting algorithms that evolve problems as well as train agents for these problems. There's this POET algorithm where this environment space is explored, where very strong curricula is emerging. The problem is it's quite expensive to run because you're keeping around all kinds of environments, and then for these environments specific expert agents that can solve these specific environments. You're not trying to train one generalist agent that can do well in all of these environments. And it also relies on a few heuristics. And then there's another approach by Michael Dennis and Natasha Jacks called paired, where you have three policies. You have an adversary that generates environments, and then you have a protagonist and antagonist that try to solve tasks in this environment. And it's a quite general method with some nice theoretical guarantees at Nash equilibrium, but it's quite a challenging optimization problem and can also lead to cycling, because basically this adversary tries to create levels that are where the protagonist can make progress, but the antagonist, where the antagonist can make progress, but the protagonist is actually falling behind. And it's just a bit of a tricky thing to optimize. So there's this paper in between the two papers I'm just talking about that we presented at NeurIPS last year, where we basically use prioritized level replay as a form of environment design by just having these buffer levels actually starting to create basically what kind of levels to use for the RL agent. I guess here the question is, do we even need to train on generated levels? Actually, we found out we can just train really well on the levels that we haven't uniformly sampled, but that come from this curriculum. And that worked really well in that it actually started to produce in this buffer quite interesting, challenging levels that are also fun, I guess, for humans to play. So these are Formula 1 tracks in the 2D car racing game. If you just do domain randomization, you get these racing tracks that look a bit like this, so they're actually not bad. If you use paired, then you actually run into an issue in terms of actually getting this environment agent co-adaptation kicked off. So it actually stays relatively simple, the levels that you get from that. But if you use these pure prioritized level replay based approaches, you get pretty challenging levels, right? With really crazy tracks that are even for humans, I think, quite hard to master. And if you have these things emerging over time, then I guess there's some hope that an agent training in this automated curriculum would actually generalize quite well. Yeah, I guess we tested this on some held out Formula 1 tracks. And we get these kind of nice policies. Here, this is I guess the strongest one here on the top left, as opposed to some policies that are trained with just domain randomization on the environment space. So this works quite nicely. But here we're asking now the question: could we actually harness the power of evolution in a very principled way to get this regret-based curriculum? So basically what we want, right, we always want to be in this zone of proximal development. We always want to be in the zone where the problems that we have in the problem space are not too easy, not too hard for the agent, but they're really in this kind of Goldilocks zone of exactly right, exactly always moving basically the capabilities of the agent. And if we have in this, for example, prioritized level replay buffer already some kind of approximation of that zone, is there a way for us to generate slightly easier or slightly harder problems from the ones that are in this frontier? And that's exactly what this method is trying to do. So rather than generating levels from scratch where we're not even sure where they lie in this space, or where it might just be very inefficient, right? Because most of them might be way too easy or way too hard. Can we actually produce more interesting levels by mutating existing levels in the buffer? Right. So these are the approaches we compared to: POET, paired, and PLR. And the approach that we developed here we call ICARL, where we have as a generation strategy, sometimes we're generating new environments from scratch, but quite often we would evolve them from existing ones in the buffer. And then the way this looks like here, for example, in NetHack, right, we have this navigation task. We had to go to this staircase down, navigating through all this lava. Is that in the beginning it's empty, the rooms in the buffer, but then over time they start to become more and more complex. Okay, so this is how it looks like. Quite similar to what I showed before, with the only difference that we also have this editor, right, that occasionally tries to do changes to these existing levels. So how does it work? So this is how it looks like, right, in terms of the curriculum over time. In the beginning, the rooms are empty, and then over time they become actually more and more structured, more and more complex. It becomes harder and harder for the agent to actually move to these goals, because these levels look more and more like actual mazes. We can track how complex these levels become based on some metrics, right, like number of blocks, or actually the shortest path for some kind of I-star algorithm to get to the goal. But the real challenge, right, is to then throw these into new environments at test time to see the generalization performance. Yes?
What is the editor able to do here? Is it modifying the description file for the environment directly? And are you storing the descriptions, or are you still storing like patches of them?
No, here it's actually directly modifying the environment, right? So it's actually putting new blocks, for example, into the environment. Yeah.
But you're still checking, is it solvable?
No, we don't have that. We don't have to do this, interestingly, right? Because the agent has a value loss. If we start to create a lot of unsolvable levels, the agents, when actually being faced with them, will predict, I can't do anything in here. And then it actually can't do anything in there. So then the value loss is going to 0, and they're going to be thrown out of the buffer automatically, because there are other levels that are more interesting. Yeah.
If the agent's only able to see around itself.
Yeah, here it only sees. I think we're starting to run a bit over time, but I think it's still interesting to discuss this. Yeah, it only sees this partial. It only has this partial view in front of it. Right? So it's actually quite difficult to navigate through these mazes, even if you play this as human, because you have to kind of keep track where you're going, right, left and right.
But the value estimate is an aggregate over the whole episode.
Yeah. And so we have all these held out test mazes, right, that have all kinds of structure, and you actually see ICARL, doing really well on all of them. And it hasn't seen any of these during training, right? And the only thing it did is actually create problems by itself during training. So I think it's quite a big deal. And then we thought, okay, well, this works quite well in these small mazes. Can we throw it at this really big one, right? And I mean, I can challenge you to try to find, just based on this partial view in front, right? You don't see actually this maze, you only see what's in front of you. Try to find this thing here at the bottom right. And you actually see ICARL being able to solve these big problems, 50% of the time. So there's a really nice example, I think, of out-of-domain generalization, right? It's following the left-hand rule, exactly. That's what it learned, right? But that's nice, right? Because we didn't teach it that, right? It figured it out by itself, and it's following the left-hand rule, and we'll eventually get to here. In the interest of time, you have to believe me that it was able to solve this. In the interest of time, let's move on. Oh, there we go. Okay. So we thought, okay, grid worlds, mazes, that's nice. But actually, what about these kind of continuous control walking problems, right? Here you have this, I guess, simulated really simple robot that should go from here to here. There are all kinds of steps and humps and pitfalls, so it's not easy to kind of navigate from the left to the right. We have this time not a way to directly modify the terrain, but actually modify some, I guess, hyperparameters of the terrain to increase the number of steps or increase the stump height and whatnot. And we again try to use the same method where we can now edit basically this description of these terrains. And what's going to happen is that, again, over time, we see automatically a curriculum evolving. So in the beginning, this is just a flat terrain. And then over time, it starts to introduce a number of steps, a number of stairs, and then slowly stumps and gaps and whatnot. So at the very end of this, the levels that we're generating for this start to become quite tough. And I think this is going on for a bit more. And then we see actually the policy in action. Or maybe not, and I have to press the next one. So here you see, after it has gone through this kind of self-generated curriculum, we see a policy that's actually quite good at navigating this relatively tricky terrain. I really love this scene where it's now really jumping very far and actually lands in the right way on its 1 foot to make it to the end on the right. Okay. I guess I'm going to skip this, but we compare this again on different and probe tasks, and we see really significant outperformance of all these kind of other autocumulative learning methods. You can play with this yourself. You can go to Excel Agent, GitHub.io. You can have all these baselines competing with this Excel Agent. You can change the hyperparameters of terrain, and you'll find some failure cases. I'm not saying this is a perfect agent, but it's, I think, a very nice example of how I think we should have interactive demos that actually really demonstrate what our agents can do and cannot do. Okay, I'm going to skip this stuff about a poet. I'm also going to skip this NeurIPS 2020 paper where we use language commentary to help exploration. And I'm going to summarize by saying that I think there's a really interesting shift away from static reinforcement learning problems, and instead of focusing on systematic generalization, I think it's a really exciting time because that means this brings reinforcement learning methods closer to real-world applications. I think open-ended learning mechanisms play a really important role in finding effective curricula. I think there will be a very important ingredient for any kind of progress into more generalist agents and more general AI. And I think language is a really interesting modality that we should start to utilize much more. If you're interested in this, Jesse Mew is presenting a paper at NeurIPS in 2 weeks on this using NetHack. And with that, I want to thank you, thank my collaborators, and yeah, time for questions.
Okay, we're gonna start with a question from. This is working now. Okay, a question from the online audience. Several questions in one. So, what do you think are the required improvements for achieving human-level performance at NetHack?
Yeah, I think it's a great question. Well, first of all, I think there's a certain debate around, can you even solve this game tabula rasa without any knowledge about external knowledge about the game? I'm not really sure where I stand on that debate, but I think if you want to have a most promising way towards solving this, you have to either tap into the world domain and common sense knowledge that's recorded by humanity in textual form. So, for example, the NetHack wiki, or even maybe all kinds of texts on the web, right, that teach you about, for example, what you can do with doors, right? This agent is really dumb, right? If it's in front of a door, you have a naive exploration strategy. It's going to try anything in this action space, which is humongous. It's going to try to pray in front of the door. It's going to try to eat the door. None of these things make sense. But you as a human, when you play this game, even for the first time, you have a certain intuition about what things you can do, right, with doors. So that's one way. The other way to get this knowledge is, I guess, from demonstrations. So we are actually at NeurIPS this year, we're going to present a NetHack data set, which is basically a very nice way for you to make use of these 5 million recorded human games. So you can look into imitation learning, behavioral cloning, and so on. The only caveat is that it's a bit like videos, so you don't actually have the actions. You have to infer those from the data. So I think it's either, yeah, learning from demonstrations or tapping into textual knowledge. Okay.
following up, what is the most complex environment in NetHack mini-grid that is consistently solved at best than human performance?
So again?
I think it's asking like which is the most complex environment in NetHack mini-grid that that is consistently solved better, like at best. The literal question is at best than human performance. I think it's asking like which one the machines are better than humans, most complex at where they are more.
I don't think there's any problem that expert NetHack players are worse than machines at this point.
Do we have versions of these games where the goal is to find whether the task is solvable or not?
So again?
Do we have versions of these games where the goal is to find whether the task is solvable or not?
Good question. I don't know anything on top of my head where you have a game where you might even at some point get problems that are not solvable. I think that makes for a really bad game and just a game experience. I think usually people like games that kind of are challenging them, but not like impossible. But I think for a beginner game player, NetHack definitely seems very impossible. So that could be one.
So
yeah.
Okay.
Thank you for the talk. Quite interesting.
For you later.
So the question I have, you said that if you have some unsolvable levels, then they won't be chosen anymore for further improvement. But this could also happen if the agent has a very bad performance. So how does this separate these two things that have the same thing?
So you're saying, okay, I guess there's one case where we would run into problems when the agent's own value estimate is really bad, but at the same time the levels keeping unsolvable, right? So the agent always thinks it can do really well, and always the level is unsolvable and it actually doesn't do well. But I think at that point, I mean, if you would hope that over time at some point the agent gets it, yeah, no, in these kind of situations I just don't have any chance to get reward. So I think unless you think that maybe over the course of optimization of this policy of the agent, it kind of gets to a point in the parameter space where it can't like escape anymore, and it's always predicting really bad values, then we would run into a problem. But unless that's happening, I think it's fine. Hopefully that makes sense.
This is not like a threshold that you have there. So it's something that after, how do you decide that it's been too long for say this is unsolvable?
There's no threshold there, right? It's really over time you would then randomly sample levels that are solvable, and there the agent would actually incur some value loss, right? Because it thinks it can't do anything, but it actually does, run into reward. Then it just so happens that level, when it's moved into the buffer, its learning potential is much higher than all the levels that were unsolvable where the agent predicted it won't do anything, right? And then they just kind of, at some point, because the buffer is fixed size, right? There's 1,000 or so levels or 10,000 levels. At some point, these levels with zero learning potential, they would just kind of be removed by better levels. But there's no hard-coded threshold. Yeah.
So you mentioned that human being would see a lower and know that you can't use it and do a lot of other things to it. Do you think that with the training model with common knowledge, or even just normal ImageNet, train on ImageNet or train on would know this kind of common knowledge and apply it to the game? Do you think that's possible to have this kind of models?
Yeah, I think it's a fantastic idea. So the idea is to basically use these foundation models that we now have in language and computer vision, see if we can kind of connect them to the RL agent such that when the agent is in front of a door in NetHack and it has this action space that also has language descriptions like, kick or open or close or lock and unlock, that we actually can get some kind of bias in terms of what we should be exploring. I think that's absolutely possible. Would be very interesting to explore that. Yeah, fully agree. Yeah. Yeah. So yeah.
So I see the advantage of editing levels, but is there an issue where like the human generated or the human created levels seem to have some structure within them, whereas the levels which you've edited or even generated by a machine seem to be very chaotic?
Yeah. Yeah, it's a fantastic question. So this is exactly, you really pointed at one of the at one of the weaknesses of current environment agent coadaptation mechanisms. There's always this slight chance, or maybe quite big chance, that this adaptation between environment and agent spirals out into some really weird part of your problem space, where it's always gradually harder and harder for the student agent, but it doesn't meaningfully correspond to any kind of things that you actually want to test your agent on. This is a huge problem. The two things I have to say to that is that I think we should be starting to look much more into quality diversity approaches that try to really get to a diverse repertoire of problems that are generated, instead of like then spiraling out into one specific area. The other thing to think about is like maybe we can also condition all this process on actual problems that we encounter in the real world. If we have these 5 million NetHack games, right, we see a lot of how NetHack levels look like. We could maybe learn how to generate those, or how to kind of bias our environment agent coadaptation to levels that look like the ones that we've seen in the actual NetHack game as well. Yeah. I don't think there were many attempts at this yet. So one attempt that we have is going to be presented at NeurIPS, so it's the stuff I didn't have time to talk about. But basically, the idea is, how do you, if you happen to have some language commentary for states, right? Could we use that to drive exploration? Because the problem with many exploration methods is that they are trying to basically seek out novelty in an environment, but in a procedurally generated environment like Minecraft, NetHack, or so, any state, almost any state you encounter will look novel, right? So you need something that kind of clusters, or gives you connections between visually very different looking states, but semantically related states. And if you have some natural language commentary for these states, which we do have in NetHack, right? You have this kind of, you just killed a gnome example, then you could actually use those as the target for these exploration methods. This is exactly what we do in this paper. But that doesn't use foundation models, right, to just get general knowledge into these agents.
Yeah, there's also a question. So I saw you run stepping in NetHack is like 25 steps per second, which is high, but it's not infinite. Is this the bottleneck in terms of research iteration for the minimal NetHack challenge? Do you know? And like, have you trying to improve the speed?
Yeah, so I mean, there are two ways to improve this. One really exciting way that kind of emerged, I guess, over the last few years, is to actually start to have environments themselves on the GPU, right? Which I think is really exciting. It's something I don't really know how we would be doing this with NetHack, given that NetHack is implemented in C and in a really big kind of code base. So I think that's probably not really possible. The other approach, obviously, is parallelization. So the numbers that you see there are on, I think, a single GPU or 2 GPUs. But you could start to try to scale this up by training on a pod of multiple GPUs, or even kind of completely, decentralized on multiple nodes with multiple GPUs. That would be nice, yeah. If anyone wants to try that, I would love to see that. I think it's probably very difficult. Yeah. Also, I mean, I should note, I mean, this relates to this kind of question about foundation models. The moment you start to throw in bigger and bigger models, obviously at some point the environment doesn't become the bottleneck, right? Like, it's the actual model that becomes the bottleneck.
Okay, so I know some of you have more questions, but we have run over time. So I think Tim is going to be here for a few minutes if you want to ask more questions now. But just to let you know, we have another seminar in 2 weeks with Hussein Fauzi to talk about alpha tensor, so faster tensor multiplication. And in 1 month, we will have Liz van der Poel from Microsoft to talk about symmetries in reinforcement learning for single and multi-agent, and reinforcement learning also for science. So thank you a lot for coming. Also, if you want to dive more into this kind of stuff, we have a reading group running every Wednesday. Feel free to come to join us or speak to any of us if you're interested. Thank you.